Hello and welcome to part one of this, the derivative as a function. So to start off, we could write the derivative formula using x to create a function as f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, the whole thing divided by h. The domain is the set of all x values where that derivative exists. And this could potentially be smaller than the domain of the function f. When x is close to 0, the slope of the tangent line is large or steep. When x is large, the slope of the tangent line is small or flat, depending, of course, on what numbers we are referencing for that. Let us say, for example, that based on this graph here, we want to sketch the graph of its derivative, right? And very helpful to make note of where, number one, where the derivative graph would cross the x-axis. So it turns out one of those is right about here at this vertex. This right here is where the slope is equal to 0. Likewise, another one is right here. Well, again, slope here is 0. And then to coordinate where everything else is, from the values here where x is negative all the way until we get to where the slope here is 0, the slope here is less than 0. But of course, it starts increasing there until we get to 0. From between this 0 and this 0, the slope here is positive, with the greatest slope being about, let us say about here-ish? About here. Greatest slope being about here, since it's where it's the steepest. And then from the right-hand side here, as after this 0 slope, the slope here decreases. And it eventually flattens out down here. To help us, again, with this particular graph, and also to make note, we have about here-ish as to where that decrease in slope is the, I don't want to say largest because we do have that left side there too, but the largest in that overall neighborhood. The graph of this will look something like this. So we would have 0 here, 0 here, and the graph would look something like this. So it would be increasing here. We cross that x-axis because it's no longer, the slope is no longer negative. It goes up to the highest point about here-ish. Again, at this particular point right here that I had highlighted. Then we decrease until we get to the 0, because the slope here is not rising as fast. So on the left side of this curve, this is where here that slope is increasing fast. And the slope here on the right-hand side here is when the slope is increasing slower. crosses the x-axis here, and then same spiel, it goes below this y-axis. We have about the lowest, about there-ish. So we'll continue on here, slightly turn, and approach this x-axis for something like that. Again, between this 0 and where this point here is, that slope is decreasing fast. And here the slope is increasing. Well, slope is decreasing slower. And eventually flattens out towards the end there. My second example, a bit more concrete. If f of x is equal to the square root of x, we want to find the derivative of f and state the domain of f prime. So from a few slides ago, that derivative f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So putting that in, so we have our function. This is the limit as h approaches 0 of, this is the square root of x plus h minus the square root of x divided by h. And now we need to simplify this a bit so we can actually get a limit. So let me do the work here for this on the right-hand side since it's a couple of steps. So let me just rewrite this function here first. So square root of x plus h minus the square root of x divided by h. So in order for this to be simplified enough for the derivative, we need to rationalize the numerator. By using the same terms in this numerator, but instead of this subtraction, we're going to have a plus. So square root of x plus h plus the square root of x. And we're going to have in the denominator the same exact thing, since we'll be multiplying by the equivalent of 1. So numerator and denominator both have that square root of x plus h plus the square root of x. So this will allow us to simplify this a bit, right? The numerator, since we have this multiplication going on here, this does simplify a bit to just x plus h minus x. That's all that is left there. And in the denominator, we have h times this whole thing. I'm not going to distribute it, and you'll see why in a moment. But h times the square root of x plus h plus the square root of x. The x's cancel in the numerator. We have h divided by h times the square root of x plus h plus the square root of x. H is here cancel. And again, the x is over here canceled. This right here makes 1 divided by the square root of x plus h plus the square root of x. So now we're going to take this that we just found and rewrite our function as that in our limit. So limit as h approaches 0 of this 1 divided by the square root of x plus h plus the square root of x. So if we plug in 0 now for h, we could do that now. This is 1 divided by the square root of x plus the square root of x. Or to simplify that nicely, this makes 1 divided by 2 times the square root of x, which is indeed the derivative of f here. For the domain though, because x is in the denominator, x can't be 0 now. but it could be any positive integer. So the domain is going to be all values starting, well, not including 0, but greater than 0 up to positive infinity. Or again, we could write that domain as the set of all x values such that x is greater than 0. But the same idea as that. When it comes to this derivative, we do have other notations. Traditional notation, y is equal to f of x, indicates x is the independent variable and y is our dependent variable. Common alternative notations for the derivative, f prime of x, can also be y prime, dy over dx, df over dx, d over dx of f of x, df of x, d sub x of f of x, all to indicate that derivative. The symbols d and d over dx are differentiation operators to indicate differentiation. They are not fractions for you to cancel things out nicely with, at least not in that traditional sense. Likewise, we have this Leibniz notation. So this is where we could rewrite the definition of the derivative as dy over dx as the limit as delta x approaches 0 of delta y divided by delta x. And at a specific number a, we can use the notation f prime of a is equal to dy over dx, where x is equal to a. And that is equal to dy over dx, again, with regards to that value of x is equal to a. So that's part 1 of this section 2.2 material on the derivative as a function. Be on the lookout for the next part. Thank you.